Good day, students. Today, let us look into how we can produce other types of polarizations in light, particularly circular polarizations and elliptical polarizations. And how can we modulate the polarizations using wave plates? How can we measure the optical activity in light and the devices used for the measurement of optical activity, polarimeters? Now, what do you mean by circularly polarized light? When light passes through a birefringent material like calcite or quartz, it splits into two linearly polarized orthogonal components. Okay. So we have, when light enters the calcite crystal, it will split into two, O ray and E ray, and they will be perpendicular to each other. Both of them will be plane polarized. If both components have same magnitude and phase difference is pi by 2, when emerging, these two beams will superimpose and the emergent light from the birefringent crystal is circularly polarized. Okay. So here, if this is the E ray and this is the O ray, while passing through the crystal, they have a phase difference. Okay. And at the end of the crystal, they will superimpose together and emerge as the circularly polarized wave. Okay, so here we have this figure where we can see that the electric field vector is traced along a circle. Okay. Now the sign of the phase difference determines the handedness of rotation. A clockwise rotation means a right-hand circular polarizing state and a phase shift of minus pi by 2. Whereas a counterclockwise rotation means left-hand circular polarization state and a phase shift of plus pi by 2. Now let us learn about the elliptically polarized light. In the earlier case, when we pass light through a birefringent crystal light, calcite or quartz, the light splits into two, O ray and E ray, and after having finite phase difference, they emerge out of the crystal. Now, if the O ray and E ray have different magnitudes, then they will produce an elliptically polarized light on superimposing. So here, when light passes through a birefringent material, it splits into two linearly polarized orthogonal components, O ray and E ray. If both the components have different magnitudes and the phase difference between them is pi by 2, the emergent light from the birefringent crystal is elliptically polarized. Okay? It will be of this nature, elliptically polarized. So the electric vector, field vector, will trace the path along this ellipse. Now, when light is circularly or elliptically polarized, the electric field vector rotates with respect to a Cartesian coordinate system as it propagates. So, in this Cartesian coordinate system x, y, z, the electric field vector will move like this, okay, like this. So, if we plot the tail of the electric field vector on a plane, it will be moving along the ellipse here. Now, what do you mean by a wave plate or retarder? It is a thin plate of birefringent material that can change the state of polarization of the incoming beam. Now, when plane polarized light is incident on such a wave plate, it splits the light into two plane polarized light waves, O ray and E ray, and one of the waves lag behind the other by a finite amount of phase after emerging from the wave plate. The two waves will superimpose there to produce a wave of different state of polarization. Now, the quarter wave plate is such a wave plate or retarder. Here, the quarter wave plate is a wave plate of birefringent crystal whose thickness is adjusted such that the optical path difference between the O ray and E ray is lambda by 4, and hence the optical phase difference between the O ray and E ray will be pi by 2. It can be used to produce both the elliptically polarized light and circularly polarized light. The optical path difference between the O ray and E ray in the crystal will be the change in refractive indices, that is mu E minus mu O into T, that is equal to lambda by 4. Hence, we can decide the thickness of the quarter wave plate. So if we have light of a known wavelength, for example 500 nanometers, we can select a quarter wave plate for that wavelength in order to change its polarization. Okay. So if we have a quartz plate with us and we need to change the polarization of a linearly polarized light to a circularly polarized light, we can decide the thickness of that quartz plate using this equation. T is equal to lambda by 4 mu E minus mu naught, where lambda is the wavelength of the given source. So in this figure we can see that in a quarter wave plate, when linearly polarized light is incident upon it at particular angle, here 45 degrees, the emerging wavefront will be circularly polarized light. Now, a half wave plate is a wave plate of bifringent crystal whose thickness is adjusted such that optical path difference between the O ray and E ray is lambda by 2. Hence, phase difference will be pi. These plates are used to change or invert the handedness of elliptically and circularly polarized light, that is, changing the right to left and vice versa. The optical path difference between O ray and E ray will be lambda by 2. So, in order to design a half wave plate for a light of particular wavelength lambda, we just need to calculate its thickness using this relation lambda by 2 into mu E minus mu naught. In this figure, we can see that if we have a right-handed linearly polarized light, in order to change its handedness, we pass it through a half-wave plate. And while moving through the half-wave plate, we can see that the rays, they split into O ray and E ray. The green is one ray and the blue is the other ray. And its phase is changing within the crystal, right? So here, the blue ray was oriented in this direction, whereas here, its orientation is changed. Its phase is shifted here. And hence, on the emergent side of the crystal, we get a left-handed linearly polarized light. Now let us theoretically derive how to produce circularly polarized and elliptically polarized light. For that, let us assume a Cartesian coordinate system where this is the x-axis, this is the y-axis, and this is the z-axis. And the crystal is placed at x is equal to 0. Assume plane polarized light to be incident on the crystal surface and the amplitude of the electric field vector is E naught. So plane polarized light is incident on the crystal surface at an angle phi with respect to the z-axis. Hence, while it emerges into the crystal, it will be resolved into two components, the O component and the E component. O component will be perpendicular to the crystal and the E component will be parallel to the axis of the crystal, and they can be written as EY is equal to, the component along the y-axis will be E naught sine phi, yes, sine phi into cos of kx minus omega t. This is the expression of a general wave. The general expression is usually given as A is equal to A naught, a harmonic function, cos of kx minus omega t. So here in place of the instantaneous value A naught, we have used the instantaneous value along the y-axis, that is E naught sine phi and cos kx minus omega t. And the component Ez can be written as E naught cos of phi cos kx minus omega t. Now, at the surface of the crystal at x is equal to 0, we get Ey is equal to E naught sine phi cos of omega t, and Ez is equal to E naught cos phi cos of omega t. Right? Now, when the light enters into the crystal, it will split into these Ey and Ez components, and they will travel at different velocities through the crystal. So let us assume that the light travels through a distance of d thickness in the crystal, and they have the propagation vectors k1 for the O ray and k2 for the E ray. Hence, we can write Ey is equal to E naught sine phi cos of k2d minus omega t for the E ray, and Ez is equal to E naught cos phi cos of k1d minus omega t for the O ray. Here we are going to use some substitutions. We have the propagation vector k is equal to 2 pi by lambda. Hence, k1 is equal to 2 pi by lambda 1. Now, lambda 1 can be substituted for lambda by refractive index of that light, of that medium. So here 1 corresponds to the O ray. So lambda 1 is equal to lambda by mu O. Hence we can write k1 is equal to 2 pi by lambda into mu O. 2 pi by lambda is the propagation vector in air, hence k times mu O. Likewise, k2 can be written as k times mu E. Now substituting that here, we can write Ey is equal to E naught sine phi cos of mu E kd minus omega t for the E ray, and Ez is equal to E naught cos phi cos of mu O kd minus omega t for the O ray. Now here we take another substitution. Theta O is taken as mu O k d, and theta E is taken as mu E k d. Hence, Ey becomes E naught sine phi cos of theta E minus omega t for the E ray, and Ez becomes E naught cos phi cos of theta O minus omega t for the O ray. Now, if we shift the time from t to t plus theta e by omega, time is shifted to t plus theta e by omega, these expressions thus become Ey is equal to E naught sine phi cos omega t and Ez is equal to E naught cos phi cos of theta minus omega t. Thus, these are the expressions for the O ray and E ray coming out of the plate. When they superimpose for different conditions of phi and theta, we get different polarizations. Here, phi is the angle at which the light is oriented with respect to the axis, and theta is the phase difference between the O ray and the E ray. Now let us take the first case when phi is equal to pi by 4 and theta is equal to pi by 2. Substituting these values for the equations of Ey and Ez, we will get the expression finally Ey square plus Ez square is equal to E naught square by 2. You can do the mathematics behind this. Here we understand this to be the expression or equation for a circle. Hence, when light is superimposing with the values of phi pi by 4 and theta pi by 2, we get a circularly polarized light. Now for the next case, if we have the phi value not equal to pi by 4 and theta is equal to pi by 2, this will give rise to an expression of the form Ey square by A square plus Ez square by B square is equal to 1. This is the equation of an ellipse, and hence we understand that the emergent ray will be elliptically polarized light. Now for the third case, if the phi value is pi by 4 and theta is equal to pi, phase difference between the rays is pi, the emergent wave can be represented by the equation Ey is equal to E naught by root 2 cos omega t and Ez is equal to minus of E naught by root 2 cos omega t. So from here we understand that the emergent ray is a linearly polarized light in which its handedness is just inverted. From this cases we understand that when light is incident upon a quarter wave plate, since the phase difference between the O ray and E ray is pi by 2, it corresponds to a path difference of lambda by 4. This is a quarter wave plate. So when light is incident at 45 degrees on a quarter wave plate, we can make plane polarized light into circularly polarized light. So when here, in the second case, when plane polarized light is incident at any other angle other than 45 degree on a quarter wave plate, the emergent ray will be elliptically polarized light. And in the third case, when plane polarized light is incident at an angle of 45 degrees on a half wave plate, okay, then the handedness of the light is just inverted. So here, let us summarize. To produce the circularly polarized light, unpolarized light is passed through a polarizer first, and then the light is made plane polarized. So plane polarized light is then passed through a quarter wave plate at an angle of 45 degrees with the optic axis. Here in the plate, the light is split into O ray and E ray. They emerge from the wave plate with a path difference of lambda by 4 and combine to produce circularly polarized light. Now to produce elliptically polarized light again, taking unpolarized light, we first polarize it by passing through it an Nicol prism. Then It is passed through a quarter wave plate at any angle other than 45 degree with respect to the optic axis. In the quarter wave plate, the light splits into two and emerges from the quarter wave plate as a elliptically polarized light. Now, if we have unknown source of polarization, how do we detect or define its polarization? For that, let us learn it. Now, to detect linearly or circularly or elliptically polarized light, we need a polarizer and a quarter wave plate. Light is first passed through the polarizer. Then the polarizer is rotated through a full circle and we observe how the intensity of the transmitted light behaves. Now, if the intensity of the transmitted light is becoming zero twice in one complete rotation of the polarizer, then that incident light is plane polarized. Now, if the intensity of the transmitted light does not become zero, but it only becomes minima and then goes to maxima, then again minima and maxima, twice in one full rotation, then the incident light is either elliptically polarized or partially polarized. And also, if the intensity of the transmitted light is constant on one full rotation of the polarizer, then that light can be either circularly polarized or it can be unpolarized. Now, how do we differentiate elliptically polarized and partially polarized light? Now, if that light is elliptically polarized, we pass it through a quarter wave plate first. Then the quarter wave plate will convert the elliptically polarized light to plane polarized light, and the plane polarized light is then passed through a polarizer. Again, when the polarizer is rotated over one full rotation, light will become zero twice in one full rotation. So we understand that the incident light is elliptically polarized. Now, again here if the light only goes to a maxima and minima, it does not become zero in the minima, then we understand that the incident light is partially polarized. Now, to differentiate between circularly polarized and unpolarized light, that light is passed through a quarter wave plate and polarizer again. Now here, if the light was circularly polarized, the quarter wave plate would have converted it into linearly polarized light. And the linearly polarized light, upon passing through this polarizer, will become zero twice in one full rotation. Okay. Now here again, if the intensity of the transmitted light is again constant, we understand that the incident light was unpolarized. Now, we understand that certain crystals have the ability to change or shift the plane of polarization of light. And this ability to rotate the plane of polarization of light by these materials is called its optical activity. If the plane is shifted towards the right, then it is called dextrorotation. And if the plane of polarization is shifted towards the left, it is called levorotation. Cane sugar, sodium chloride are dextrorotary materials, whereas turpentine, fructose are levorotary materials. Now, to study the optical activity in materials, we use a Laurents half-shade polarimeter. It consists of a monochromatic source light S, and then we have a convex lens L. After the lens, there is a polarizer Nicol prism. Then we have a half-shade device. After that, we have a glass tube in which we fill the liquid of which we have to study the optical activity. And after the glass tube, we place the second Nicol prism. It acts as the analyzer. And after that, we use the telescope to view the light through these. here the rotation of this analyzer will be measured. First, we rotate the analyzer such that it is dark when we view through this telescope, and the noting on the circular scale is taken. Then we fill the glass tube with this optically active solution and keep it aligned with the optic axis. Now, initially when we had viewed this apparatus through the telescope, the field was dark. But after filling the glass tube with this solution, we see that the solution has rotated the plane of polarization of the incoming light, and hence light through the analyzer will now be bright. Now the analyzer is again rotated by a certain angle theta so that it becomes dark again. This angle is noted, and the difference between the earlier angle and this angle will give the angle of rotation of plane polarization theta. In this apparatus, we have made use of a half-shade device. Let us see that in detail. The Laurents half-shade device consists of two semicircular plates. One half is made of glass, while the other half is made of quartz, and both are joined together. Now the quartz is cut such that it is along the optic axis. Its transmission axis is parallel to this joined axis. The thickness of the quartz is selected such that it behaves as a half-wave plate. The thickness of the glass is selected such that it absorbs the same amount of light absorbed by the quartz half. Now let us assume that light is incident on this half-shade device, and the angle at which light is incident is along this P prime P axis. Okay. So light is incident on this angle. The portion of light passing through glass will transmit as such that it will be along OP axis, whereas the portion passing through the quartz plate, here double refraction takes place and the light will split into two. The O ray and E rays will be along the different axes. That is, E component will be parallel to this optic axis. It will be along OY, and O component will be along OX. Okay, that is, the direction of the ray is in this direction. It is directed from P prime to P. Okay, so on resolving, it will be along these two directions. Okay, now what happens is, in the half-wave plate, the E ray travels as such, whereas the O ray experiences a phase difference of pi. So the O ray will shift from OX to OX prime. So then what happens is, we have the E ray along OY and the O ray along OX prime, and they will resolve together to form the resultant along OC. So in the glass portion, light will be aligned along OP, whereas in the quartz portion, light will be aligned along OC. Now, if we have the Nicol prism aligned along OP axis, what happens is, the light passing through the glass portion of that half-shade device, it will pass through that Nicol prism. Whereas light passing through the quartz it was aligned in this direction, right? And that will be blocked by this Nicol prism. So here it will be dark, whereas here it will be bright. Now, if the Nicol prism is rotated along this axis, CC prime, it will be parallel to OC. So the light passing through the quartz region will pass through it, whereas light emerging from the glass region of the half-shade device will not be able, that will be in this direction, OP. It will not be able to pass through the Nicol prism, and hence it will be dark here and bright here. Okay. Now, when the Nicol prism is oriented along the axis YY prime, okay, then it will pass some amount of light from the glass portion and also some amount of light from the quartz portion. So it will be equally bright. Whereas if the Nicol prism is aligned along this direction, it is aligned along x prime, it will completely block the light from glass and quartz, and hence it will be equally dark. So using this half shade device, we can increase the accuracy of detecting the regions of darkness and regions of brightness in the polarimeter. That's all for today. Thank you.